Welcome everybody to this talk in the weekly CSIG series that happens usually at 10:30 a.m. US Eastern on Thursdays. Today we're having the call at 8:30 a.m. US Eastern on Thursday, 10th of October. We've got Nick Pentarif going to speak to us about standardizing deep learning model deployment with the Model Asset Exchange. So I'll hand over to you, Nick. Go ahead.
Thank you, Susan, and hello, everyone. I'm Nick Pentarif, Principal Engineer at IBM. A little bit about me. I'm MLNick on Twitter and GitHub. I work at IBM in a team called the Center for Open Source Data and AI Technologies, or CODA for short. I focus predominantly on machine learning and AI applications and open source projects, and have a long background in the Apache Spark project, where I'm a committer and PMC member. So before we get started on the topic for today, very briefly about the CODA team. We're a team of over 30 open source developers and advocates working to improve the enterprise AI lifecycle out in open source technologies. And this covers a range of projects, including Spark and the various deep learning frameworks, as well as model deployment standards, AI fairness, trust, and explainability projects, the Python data science stack, and some of the projects, one particular project that we're going to be talking about today, the Model Asset Exchange. And we'll be talking about how we deploy models in that exchange and the framework that we have for wrapping them and deploying them. So a little bit about the machine learning workflow. The workflow is a complex one that spans teams and organizational boundaries. So we start off with the data ingestion and management phase, which is the purvey of data engineers. Then we have the data science and research sub workflow, which is the one that we all associate with model building and the data science process. And that's in taking the data from various sources into that process, doing data visualization and exploration, feature transformation, pre-processing, the model selection and evaluation piece, and then finally actually deploying that model. A lot of the discussion ends there at having trained a machine learning model, but without being able to deploy it into the real world and a live system, and for it to actually have impact, there's not going to be much use there. And once it's deployed, that's typically the domain of the machine learning and production engineers. So you have this complex workflow, which is in fact a loop, because once the model is out there, it's creating new data and it's making predictions and it's having an impact on the world around it. And that's creating a feedback loop, which is coming back into the data, the first phase of the workflow and the data side. So this loop spans teams, and it also spans many different tools, open source, proprietary. There's a wide variety of data formats, machine learning and data science toolkits for each step in this phase. And finally, this workflow and this entire machine learning piece is a very important but very small piece of the actual puzzle when we look at the full machine learning system. So that the ML code itself, while it gets a lot of attention and is important, really needs to integrate with all the different pieces of an application. And in particular for deployed models, what's important here is serving infrastructure, analysis tools, monitoring. So when it comes to machine learning deployment, we have to answer three questions: the what, the where, and the how. So what are you deploying? What do we mean by a model? Where are you deploying it, and how are you deploying it? Today we'll talk mostly about the what and the how, starting with this first question, which is what are we deploying? What do we mean by a machine learning model? So in most cases, what people think about a model is that it's just this trained algorithm, a set of weights that have been trained on data, and we can just deploy that. But in fact, there's, as we saw previously, a lot of steps that come before in this workflow. We have to extract and transform data. We have to do feature extraction and engineering and pre-processing of those features to get this raw data into a format that can actually be trained by a machine learning model. And the algorithm takes in typically vectors or tensors, numerical data, but a lot of the the raw data that we have in real world applications is of all different sorts: text, image, audio, some numerical, categorical. So if we do not apply exactly the same pre-processing steps during prediction as we do in training, we're basically going to get a garbage in, garbage out situation. So we need to ensure that we actually do exactly the same pipeline of steps at prediction as we do in the training. And we've all heard about deep learning, and we're talking specifically about deep learning deployment today. And the common perception here is deep learning doesn't need any feature engineering or data pre-processing. We don't have to worry about those previous phases. Correct. This is the common perception of how deep learning works. We just throw in this raw image, we run our deep learning network, and we get out a prediction. But the reality is a lot more complex. And when you actually look at these pipelines, they look very much the same as all other machine learning pipelines. Yes, we start off with raw data, but before we can pass it into the inference phase of our deep learning model or architecture, we still need to do a lot of image pre-processing. So we need to decode the image, potentially do resizing, normalization, conversion of types and formats. And this is typically done with a wide variety of image processing libraries: Pillow, OpenCV, scikit-image, TensorFlow images, image module. There's many of them that are common. Once you have that, then yes, we can pass it through our favorite framework for doing inference. But even then, what comes out of that is typically a tensor of predicted probabilities, which is not very useful in a real-world application. We need to do post-processing of that tensor to get it into a format, for example, JSON, that can be that can allow us to integrate into an application and allows us this model to integrate into that wider system that we saw before. So in reality, deep learning needs to take into account these pre- and post-processing steps, just like all other machine learning. So we really need to think about deploying not just the machine learning model or the algorithm, but the entire pipeline. So the data transform, feature extraction, pre-processing, the model itself, as well as the post-processing of whatever that prediction is, to get it into a both human and application readable format. So there's many challenges that come with deploying models, and we need to, some of them on the need to manage and bridging many different frameworks, languages, dependencies, versions, almost too many to count. You can see this zoo of framework logos here, and this is just a fraction of them. Friction between teams, and a proliferation of different formats and different APIs across all these frameworks. Each one does things slightly differently. And you have this lack of standardization, which inevitably leads to many different custom solutions for each particular deployment. So one way that we can start to address this challenge, and one of the approaches that many out there have taken, and we have taken with the Model Asset Exchange, is containers. And container-based deployment for software has become very popular for many reasons, and it's found its way into machine learning for deployment. So there are many significant benefits for using containers for deployment. You have repeatability, there's ease of configuration. For me, one of the key benefits is the separation of concerns. You can separate out the what and the how, so to speak. So data scientists can focus on the what. They can use their favorite framework, and they don't have to worry necessarily exactly how that's going to be deployed. They can put that model into a container, and the production engineers can worry about the how. How is it going to be deployed? What cluster environment or framework? Which cloud target, on-premises, hybrid cloud, whatever the case may be. And the data scientist doesn't have to get bogged down in those details. They can simply wrap something up in a container and pass it over the wall to production. But that doesn't solve all the challenges. Answering that what question is still very critical. What goes into that container is a very important factor for many reasons, including performance and this issue of standardization. So if we just simply wrap up Python code, it may not be very performant, but maybe it's scikit-learn or it's TensorFlow, and then the performance would be good. So without really inspecting what's in that container and understanding it, it's very difficult to know that. And when it comes to production service level agreements or requirements for latency, these are all critical factors. It also doesn't solve this issue of standardization. So just because you have a container doesn't necessarily mean you know how to access that model. How does the rest of your application, the rest of your microservice architecture actually interface with that model? So you still need to standardize the formats and the APIs exposed, and you still need a serving framework on top of all of this, even if you're using containers as the base building block. And this is really what the missing piece that we're trying to solve here with the Model Asset Exchange. So MAX, or the Model Asset Exchange, is a project that we started out of the Code A team about 1.5 years ago to provide a centralized one-stop shop, one-stop repository for best-of-breed open-source deep learning models. So it's a place where you can find these state-of-the-art deep learning models across a wide variety of domains, including image processing, text, speech, audio, NLP, a wide variety of domains that are popular with many application developers and use cases. A big part of what we're trying to do with Max and Model Asset Exchange is to vet the code and the IP that goes into the models. So a lot of the time, you may be able to find a model that's been published by a research group or by academics or by a corporate lab, but it's very difficult without really diving into that model code on GitHub and testing it and walking through it to know if it really works, if it really does what it says on the tin. Another issue that one has to take into account is the intellectual property and the licensing. And this includes licenses attached to data sets for training, for the model code, for the model weights, and you often have different components licensed under very different license agreements, and all of this needs to be checked and vetted. So all the models that go into Model Asset Exchange have had this vetting done for you effectively, and you can rely on the fact that they're released under permissive open source licenses. And the final point is that we have both pre-trained models on Model Asset Exchange, as well as more recently ones that can be trained, custom trained on your own data. We won't be talking about training today, mostly about the deployment side. But you can find trainable models on Max. So behind the scenes, I alluded to this process of putting models onto the exchange. And the process starts with going out and finding what is the state-of-the-art model out there for a specific use case or domain. Object detection, segmentation, captioning, for example. This vetting and validation of license terms, as well as the code cleanup, testing, refactoring work is a significant amount of work that goes into ensuring that the quality of the models on the exchange and the licensing terms quality is high, and the licensing terms are correct for use in an enterprise application. And then the models are wrapped in our Max framework and exposed as standardized REST API, and then published as Docker images on our Docker Hub. And then there's a continuous review and integration, effectively loop that comes at the end of it to ensure that the models continue to work as expected, that they're updated with the latest releases and so on out in the open source community. So this middle step of wrapping models and with a framework is what we'll talk about for the rest of the talk. So if we dive into what is this asset that we talk about, what is an asset on the Model Asset Exchange? For deployable models, we effectively, to create this model, we need to combine the data, the model architecture, the compute power and expertise for fine-tuning or hyperparameter optimization, network architecture, and all of that. We combine those together, and we get this pre-trained model and the set of model weights. Together with that, as we saw previously, we need to be very cognizant of the pre-processing and post-processing code that is part of this pipeline. and then we expose the end result as a REST API in a standardized manner that is easy to consume in an application. And that is a deployable asset on the model asset exchange. It's the pre-trained model, the pre and post processing to take raw data through to model inference, through to usable output in an application friendly form, as well as a Swagger or Open API specification and metadata endpoints that allow you to understand more about what is the model license, the use case, the application. And the Swagger or Open API spec allows us to create user interfaces for API exploration and the capacity to, for example, auto-generate API clients that can communicate with that model. So the model APIs exposed are typically of two forms. Get endpoints that allow things like metadata requests, or in many cases for classification models to get information about what are the labels that the model that are part of the model, and then post requests where information for inference is sent to the model. So an image in the case of a image classifier or object detection model, a piece of text in the case of NLP, and so on. So that this is the Swagger user interface, which allows you to actually explore the typical endpoints. So for one of our popular models, the object detector, you can see that there's two standard endpoints to get the labels that can be predicted by the model, as well as the model metadata, and a standardized model predict post endpoint, which we use for making predictions. So this makes it very easy to call that model in Python using your standard tools. And here's a link to a notebook which walks through how to use Python API calls, REST API calls, to interact with some of the popular Max models. And the response that we get is a standardized JSON response that can be very easily integrated into an application, and both human readable as well as application or machine readable. To go with the Max models, we typically also, for many of them, create sample web applications, which either in Python or JavaScript or a combination, which illustrate how to easily consume these APIs in an application. So that really is showing developers how to go from the structured JSON output that is standard for the Max API to create an application that can do something something useful. In this case, our object detector sample app just draws bounding boxes around the objects in the image. And there are many other ways that we also expose to consume these models. So Node-RED for IoT applications. We have code pens for consuming the models in JavaScript for those that are TensorFlow.js models that we have ported over, and many others. So we've seen how we've attempted to standardize the set of APIs and the way that models are exposed via these APIs. And the way that we achieve this is through two small projects. The first is the Max framework, and the second is the Max skeleton. So the framework is a small Python library, essentially a lightweight wrapper around a common Flask functionality for Python APIs. And we try to abstract out all the common functionality and common code across Max models. And the two main base classes are we have a base Max API and a base Max app, which take care of a lot of the boilerplate. And the Max skeleton is a GitHub repository that is actually a template repo, which allows you to very easily create a new Max model, effectively wrap up a deep learning model for deployment. And it takes care of most of the boilerplate for doing that, and provides the skeleton code where it's very easy, quick and easy to fill in the blanks and create a new model. So this really eases and speeds up the life cycle of going from a pre-trained model that has been vetted and known to work, to actually wrapping it up and deploying it as the standardized API within a Docker container. So the Max framework model wrapper is the main class that encapsulates the model-specific logic, and it's fairly simple, exposing some metadata information, and then 3 standardized methods for pre-processing the input. So that's taking the raw input and effectively creating a set of tensors which are going to be passed into the core deep learning model, that inference phase is in the predict method, and that typically is going to be wrapping your TensorFlow save model or PyTorch model or Onyx model, whatever the case may be. And then post-processing the result is typically going to be converting the tensor output from that predict phase, that inference phase, into a standard JSON response. So these are simply the 3 methods that have to be implemented, and the rest of the boilerplate is typically taken care of. And within the initialization of the method is the model loading, typically from the standard format for whatever library is being used. And on the API side, again, as much of the boilerplate as possible is taken care of, so that only a few lines of core logic have to be implemented to take the raw input of the API, for example, an image or piece of text, pass it through to parse that input and then pass it through to the model wrapper, and then do some post-processing of the response to get it into the correct format. And then the final component, which is a recent addition to the framework, is specifically for image applications. What we found is there are many common functions that were required across all the different Max models that deal with images, and the underlying code, the underlying research code where those models came from, typically used various libraries. Some used OpenCV, some used Pillow, some used scikit-image, some used TensorFlow image module, but they were all doing much the same thing. As we saw previously in the deep learning workflow diagram, most of the time these common steps include loading or parsing the image, doing things like resizing, cropping, normalization, and so on. So we created an image utility within the Max framework that very much mimics the way that PyTorch Vision, Torch Vision transforms work, but that are independent of the PyTorch dependency and allow us to use the same set of code across all Max models. So again, just trying to abstract away as much of the common functionality and the boilerplate as possible. So because we've created this set of lightweight wrappers and this framework, it makes it very easy for wrapping a model. And packaging up as a container for either for deployment on Max, or if this framework is obviously public on GitHub and free for anyone to use if they want to take the same approach for creating their own models. So as long as you have Docker and a set of pre-trained weights, all you have to do really is fill in the input pre-processing code, the core inference, and the output post-processing code. Make a few small adjustments to the Docker recipes and the API metadata, and you have a model API ready to go as a Docker container. And you can actually use the Max skeleton template repository to do this. So because it's a template, you can just simply click on the use as a template button in GitHub, and it'll pre-populate a new repository using that template code. And you just fill in the blanks with a Docker file, any Python requirements, metadata, as I mentioned, the pre and post processing, as well as inference code, and then the set of tests that we have as standard as part of our continuous integration setup, which is testing the model inference code, as well as the API the API code handling of various inputs, correctly handling invalid user input or erroneous input, and ensuring that the outputs are in the correct form. Okay, so we've gone through all the details about the way that we wrap models and within the Model Asset Exchange and the high-level framework that we've created. There's a bunch of links here that I've listed here to go and find Max on the IBM developer site. There's a lot of learning resources. You can see the learning path, for example, is a detailed tutorial about how to use Model Asset Exchange. And on the main Max page, you can find a wealth of information about the project, the different models, how to use it, how to use them, how to integrate these models into your applications in Python, TensorFlow, Node-RED, IoT, and so on, as well as the Max framework and Max skeleton, which are public. And we have another recent project called the Data Asset Exchange, which is analogous to what we're trying to do or have done with models in creating open data sets, a one-stop place to find open license data sets for use in enterprise applications, featuring many data sets coming out of IBM research. So I encourage you to go and have a look at the Data Asset Exchange as well. Thanks very much.
Thank you so much for the wonderfully concise and detailed and clear talk. Very nice. I see some questions in the chat. How can we access the Max repository? I can put the link in the chat. Is there an exhaustive list of all the models deployed in Max? And could you please emphasize the main performance differentiator between wrapping a deep neural network model in Max and using it directly in Watson Studio local cloud? So if you want to focus on the third question,
right. So
right, and I'll do the other ones. And okay.
Okay. I posted the link for Max there, ibm.biz/model-exchange. So Max is completely free and open. And on that page is listed all of the models on the exchange. I think in excess of 25 models at the moment, with more always in the pipeline. Our team is always looking at new and interesting use cases. So in terms of the performance differentiator, I mean, between wrapping a model in Max and using it directly in some other application or in Watson Studio in particular, really the core underlying inference is done in the framework of choice. Most of our models are TensorFlow, but we also have PyTorch as well as Onyx. Now, the pre and post processing code that happens is typically fairly standard Python code. So there's very little difference in raw performance between deploying that as a Docker container on, for example, Red Hat OpenShift or on IBM Cloud or Kubernetes cluster on IBM Cloud, and using doing the core inference on the Watson machine learning service, for example, because they're effectively running the same thing. Obviously, a lot will depend on the particular hardware or setup that one has, GPUs, etc. At the moment, we don't support deploying the full model with pre and post processing code to Watson machine learning, but that is something that we're looking at. But I would expect that one wouldn't see significant differences in performance. It really depends on what the particular technology stack that you're working with is. So if for example, one is very heavily invested already in a Kubernetes setup, with a Kube or OpenShift cluster already running a set of microservices, then it may naturally make sense to Dockerize and go that route. If one is already using various Watson APIs and WML, it may make sense to go that route, or have a mix. It's really there's no one answer. I would say it really depends on the particular setup.
Thank you very much, Nick. I assume you're okay with that, Sarah. And there was another question asking to compare Acumos with Max. I can do that. I can see one or two people on the call who can also do that. But do you want? I'm not sure how familiar you are with Acumos, Nick.
Somewhat familiar with Acumos.
Oh, go ahead then, please.
I confess that I haven't looked at it for a little while.
Yeah,
so I
please
actually
go
need
ahead.
to refamiliarize. I need to refamiliarize myself a little bit. But I think many of the goals are quite similar. In the sense of trying to have a centralized, place or repository and form for hosting models and discovery, as well as standardizing on the formats and the way things are wrapped up and exposed. So I think there's a lot of commonality there. And there may be scope to actually, work together or look at ways to integrate. I would say one difference at the moment is I believe that certainly a goal of Acumos, I'm not sure if it's sort of achieved as yet, but one goal was to be able to provide a potentially an internally or privately hosted version of a model repository. That is something that Max has not tried to do. We are purely, one site and purely on the open source side at this point. So there's no capacity or no way to have an internal version of Max for your organization, for example. Whereas I think Acumos is trying to be more general in that sense.
Yes, I would agree with you. Acumos is about creating your own marketplace and hosting it, let's say, internally. And the models themselves don't have to be open source. They can be any kind of model. With Max, it's a single deployment of a model of a repository of models, and the models themselves are open source. Any more questions from anyone? Oh, there's another question. Have you looked at papers with code? Thoughts?
So yeah, I see Jim mentioned papers with code. I think it's really interesting what they've done there. And the key difference, I would say at the moment is papers with code provides a great way of discovering the state of the art models, and they're doing a lot of great work on standardizing the way that the metrics and results are kind of updated into leaderboards, so you can very quickly find out what is the latest state of the art performance, as well as what is the kind of historical evolution. Typically, the papers with code, the with code part of it, is a link to a GitHub repository. Now, that GitHub repository could be, it could be anything. It could be a fully fledged framework for object detection that includes containers and APIs and the whole lot, or it could just be a piece of research code that from a paper that's been kind of dumped into there and not necessarily maintained. So I think the focus rightly for them has been on the front end side, effectively the discovery and surfacing the leaderboard results, but not so much on the back end of okay, how do we go from here's a new state of the art model to here's a new state of the art model wrapped in a standardized API that can be consumed by my application without necessarily needing to know much about the underlying deep learning model itself. And that's what Max is trying to do. So I see a lot of some commonality and a lot of kind of shared vision. And I think there's many interesting ideas about how can we go in a more automated way from there's a new state of the art model that's been surfaced on papers with code through to wrapping that into Max. So I would say that's the contrast between those two. I think they're trying to achieve slightly different sides of the same coin, so to speak.
Thank you very much, Nick. And please, those on the call, please thank Nick if you enjoyed the session. I'm also interested in knowing if you prefer this time at 30 a.m. US Eastern. Certainly, I prefer it, and I'm interested in what people's opinions are. So please post in the chat your thank yous and an indication if you prefer this time of day. And I'll close the call now and say goodbye.
Thank you, Susan, for the opportunity, and thank you everyone for your time.
Thank you. Thank you all.